Dear students, this is tutorial number 5. You are going to visit one important distribution in addition to the ones you have learned in tutorial number 2 or number 3. This distribution is called Poisson distribution. We are going to focus on Poisson distribution because this distribution is very important in network modeling. You have to pay attention carefully to what I'm saying because it's not easy to understand this type of distribution. Often we are interested in the number of events which occur in a specific period of time in a specific area of volume. So we have two independent variables here, time and area, or the volume of this specific you are going to talk about, which is Poisson distribution. The Poisson distribution has a famous formula. It says the probability of x in a specific time in a specific area can be measured by using this simple formula. This is an approximation formula, by the way. For example, lambda here is the average, the mean value of this speculation or probability. X here is the occurrence of this event. So you have two parameters to calculate the probability of x, lambda and x. Okay. Let's see what some examples of Poisson distribution in our real life. For example, the number of alpha particles emitted from a radioactive source during a given period of time is an example of a Poisson distribution. Number of telephone calls coming into an exchange during 1 unit of time, such as if you have a cell tower next to your house, how many number of calls you are expecting to get in a specific, for example, between 5 p.m. and 6 p.m. The number of telephone calls is not exactly the same every day, but it follows Poisson distribution. Number of disease trees per acre. Acre is like an area. Usually we say it's about like less than 1 square kilometer of a certain woodland. How many infected or trees in your in a specific area you have. Number of death claims received by day by insurance company. This is another example of Poisson distribution formula. Look, these examples, they are not following Bernoulli's or other types of distribution. They have their specific natural way to happen. For this reason, we are using exponential here, because everything that's related to natural in happening, not infected by other means, by other factors, usually follows exponential behavior. Okay, let's see some characteristics of Poisson distribution. Let x be the number of times a certain event occurs during a given unit of time. The number of times occurs in a specific unit of time or in a given area, etc. The probability that the event occurs in a given unit of time is the same for all the units. This is one characteristic of Poisson distribution. The probability of that event that occurs in a given unit of time is the same of all the units. It means that they are equal probable in this specific time. The number of events that occurs in 1 unit of time is independent of the number of events in other units of time. This is another characteristic of Poisson distribution. The mean or the average, or in statistics they call it expected value, rate is lambda. For example, how many times it rains in the winter in Iraq? Say 10 times per year or 20 times per year. This is the mean, because you have calculated this mean by using many years. But how many times will it rain next year? in 2021, for example. You don't know that, but it will follow the Poisson distribution. Okay. Then x is a Poisson random variable with parameter lambda, and the frequency function of this probability function, the frequency function of this x, is related to the average mean to the power of x divided by factorial of x multiplied by exponential to the negative value of the mean, where x is 0, 1, 2 number of times. Okay. For number of times of 0, what will be the value of x here? Factorial of 0 is 1. Lambda to power 0 is 1. So it will follow just the average value if the number of times is 0. So it's going to be a constant value. But we don't use 0 all the time. We use many times, for a few times, 5 times, etc. We will see Poisson distribution more clear by using this different examples. Okay. Now we are going to explain what is Poisson approximation. Poisson approximation, actually, the equation you have seen here is an approximation to a derived equation. Okay. The Poisson distribution is often used to an expression for binomial probabilities. We skipped binomial probabilities, but we are now going to visit it again. But we are not going to use binomial probabilities because there is an approximation using Poisson approximation to deal with it. Okay. Probabilities when n is large and theta is small. The probability value for the binomial for x is the combination. To review about combination, these two big curvy, circular brackets means combination. If you don't know combination, from this is a review for combination. Combination has two parameters: number of trials, or the selected number of trials. So the total number is n, and the selected number is r. So you have the combination nr factorial of n divided by the multiplication of factorial of r multiplied by difference of n with r. While permutation is different. Permutation does not have this parameter, factorial r. Okay. And in the literature, there are many forms of using combination. Combination may be represented like this, just like in this equation, nk, which equals like c to nk, or sometimes they call it like nk like this. And the rule of combination is the same like as in the above, and factorial k factorial n minus k factorial. So this equation can be approximated using Poisson approximation to the same value of this by using the mean value. Hence, there is no n here. We don't have n here. So we eliminate n because the n is very large here and theta is small. We eliminate n and theta by using Poisson approximation. For this reason, Poisson approximation is very important to study, and because the equation is not that difficult and can solve many everyday's life. Okay. The value of lambda here is n multiplied by theta, but usually we can make out or find out lambda, but by other means, by statistics or without knowing n and theta. Okay. But don't forget that if you have n and theta, you will find lambda. Okay, but this is an example of to describe Poisson approximation. Fatalities, number of deaths in Peruvian cavalry. It's an old war. They used like horses and swords to fight each other. A classical example from born in 1898. They have noticed that number of fatalities resulting from being kicked by a horse, by an accident means, is 200 observation, so 200 times 10 corpses over a period of 20 years. So in the last 20 years, they have observed 200 average observation, the number of people killed by a horse kick. In average, 10 corpse. Corpse here means like a body or dead body over 20 years. So it doesn't mean that the first year was 10, the second year was 10. No, this is the average value. So you don't know what exactly the next year will be: 9, 8, 10, 15, etc. So it will follow Poisson distribution. Let's take a real mathematical example of Poisson distribution. Okay, we have the mean number of power outages in a city of Brunswick or any city is 4 times per year. This is very good in comparing to Iraq, of course. 4 times per year, there's the mean number of outages. It does not mean that each year will the outage there will be 4 outages. This is the mean number of outages. It may be 5, 6, or 3, 2, or none at all. Find the probability that at a given year there are exactly 3 outages and there are more than 3 outages. Look very carefully. So the average value is 4 outages per year. But what is the probability that next year will be 3 outages or any given year? Okay. This follows Poisson distribution. These kinds of questions, problems, because we have an average value, a mean value, lambda, and we have a specific number of steps or times, which is the number of outages. Okay, to solve this problem, in some literature they use mu instead of lambda. They are the same. They are the same rate. Okay, the mu here, the number of outages is equal to 4, which is lambda as well. Don't confuse about lambda and mu. They are the same. But some sources they use mu. Some sources they use lambda for the average, for the mean value. Okay, the required outages is 3. So using this equation, we have lambda, we have x, so follow the equation. Okay, 4 lambda to the power of 3 multiplied by, this is very important number. This is actually exponential. You usually don't see this number because it's in the calculator all the time. So you just press minus lambda exponential, you will get the same results. But more importantly, if you have number 1 here instead of this, so you have to write e. And instead of e, this is the natural number, 2.71828. You have to memorize this number. You want to have a question in the quizzes or the final exam about the number e. Okay, using the calculator, the probability of there will be 3 outages is about 19%. So it is very low. The probability of getting 3 outages per specific year is about 20% of 19.5%. Okay. The probability there will be more than 3. Be careful if you see these types of words, more than. More than is not a specific number. So we can't follow this rule exactly. Why? Because it might be 4, it might be 5, it might be 6, it might be 7. We can't compute each number. It might be 100. So instead of using more than, we know the number of less than. Okay. So instead of using more than, we will have simple trick. Okay. Probability of more than 3 is equal to 1 because you know all the summation of all probabilities is equal to 1. So we will use reverse probability, which is instead of using more than, we will use less than, but instead we will inverse, we will divide, have the difference between 1 and the probability of less than instead of more than. We know this number is easy to calculate. Why it's easy to calculate? Because you have 3. You can calculate the probability of 3, probability of 2, probability of 1, probability of 0 easily. But you can't calculate, it's difficult to calculate probability of 4, 5, 6, 7, 8, 9, 10, etc. because it says more than, and it's not undefinite number. But we usually go to the solution using simple methods. Okay, instead of using more than, we convert the more than to less than, but instead we take the difference from number 1. So for probability 3, we already have it, 0.195. Probability 2, use the same equation, you'll have this result. Probability of 1, use the same equation, you'll have this. Probability of the 0 outages is very little, it's 0.08. The summation of these probabilities is 0.567. So you have 50%, you will have almost 50% more than 3 outages, which is good because the average value of outages is 4, so 4 should be 50-50. Okay, if you calculate the average value with 4, it will be 0.5. Let's do that as a trick. If you try it by home, apply 4 here instead of x, see what will happen, what we will get instead of this number. You should get like something about like 0.5. The probability of getting 4 outages should be 0.5 because it's average value. Okay, let's jump to another example because this equation is sometimes based on the problem. You have to see the problem from the different views. Okay, this problem is related to websites and networking. Okay, the number of hits on a certain website follows a Poisson distribution. This is number of clicks. Okay, with a mean rate of 4 clicks per minute. You have a server, you have a website, and visitors are visiting your website in average 4 clicks or 4 hits per minute. What is the probability that at least 63 hits are received in the next 15 minutes? Okay. Be careful. We have the average lambda here per minute. So be careful to the like unit size. You have to regulate or scale your average before solve this question. Okay, in this problem we need to adjust lambda. Okay, since the average rate of hits is 4 per minute, so in 15 minutes the average rate will be 4 multiplied by 15. That's easy. So the average rate for 15 minutes is 60 instead of 4. So we in the distribution law of Poisson process, we are not going to use 4. We are going to use 60 because it will require how many, at least there will be 63 hits in 15 minutes, which is the average. The average is 60 hits per 15 minutes. Okay. Okay. Because we have at least here. Pay attention. Probability of x is greater or equal to 63 is very difficult to calculate. Why? Because you have to calculate the probability of 64, 63, 65, 69. Maybe you will have 1 million hits per 15 minutes. So instead, we will use the same trick we used in this previous example. We can use, we will have less than 62, but we'll use inverse probability, 1 minus probability of x, less than or equal 62, which is equal to simple distribution. Like you will use the same problem. You choose only 62 because if you got 62, it means that you got at least 36. This is a fixed number. So if you have 62 or equal to, you'll get at least 63. So you don't have to calculate 61, 60, 60 or 59. Why? Because 62 is sufficient to get you at least 63. So we will follow the same thing here. Exponential lambda is, lambda is 60 and x is 62. The value will be 0.9934. So you have 99% at least have 63 is received in 15 minutes. If you have any question, just ask me, because we have our quiz this week or maybe in the next week for such Poisson distribution.